Let's talk about the geometry of spur gears. And spur gears are the simple, common type of gear where the teeth are straight and parallel, and they are parallel to the center line of the shaft that goes through them. And an important point to note about spur gears is that when two gears are in mesh, their shafts are parallel. Next week we'll have a very short quiz about gears, and I'll ask you about that. So just make a note that their shafts are parallel. Now, when we have gear teeth coming together, we have to have the speed ratio staying constant. So for example, if we have a pinion with 20 teeth and a big gear with 40 teeth, what is our speed ratio? It's 2 to 1, isn't it? And that speed ratio has to stay 2 to 1 as both those gears are turning. It can't be a little bit under 2 to 1 at one point and a little bit greater than 2 to 1 at another point. The gears would just chew each other up if that happened. So in order to make this a consistent gear ratio as these things are whizzing around, they have to have an overlapping action where, I don't know if I have a picture yet, I will later, where as one pair of teeth are coming out of mesh, the next pair of teeth is just coming into mesh. And the way they do that is with this curving action. This meshing action is called conjugate gear tooth action. You don't need to remember that, I'm just telling you. And there are various sorts of curved tooth shapes that could give us that conjugate action so that the gear ratio would stay constant all the way along. In the olden days, people used a cycloidal shape, and that's the shape that we found in Model T car transmissions, for example, and we still find in clocks. Modern teeth use a different shape. It's called an involute, and that's the shape you see in this picture here. The involute is made this way. Now there's a mathematical formula, but if you wanted to make an involute curve physically, here's how you would do it. You'd cut a circle, maybe cut a circle out of plywood or cardboard or something, and pin a piece of string to it, and put a pencil through the end of that piece of string, and wrap that piece of string around that circle. Oops, sorry. As that string wraps around the circle, that pencil will trace this constantly changing curvy shape, and that curvy shape is called an involute curve. And the circle that you've got the string wrapped around is called the base circle. And you can see here at the bottom an illustration of some kind of pencil beginning to trace those involute curves. Now this base circle is not a physical entity. It's a mathematical location. We could use it to draw these things in CAD if we wanted to, but we're not going to. Let me see. So let's think a little bit more about involute curves. This is an excerpt out of an early 19th century engineering class demonstration mechanism. It had various kinds of machine elements in it, and one of them was a friction drive, where you could picture this as stiff brushes or two wheels made out of clutch material or some kind of friction. And you press those together, and the point where they come together is called the pitch point. You know about the pitch point. And when one of them turns, it drives the other one. Okay, now take some kind of belt and wrap a belt around those two friction circles. And now cut that belt at some point in here. And if you were to attach a pencil to the cut end of the belt, you could wrap it up around that circle and make an involute curve. Well, the angle between those two friction discs is a thing called the pressure angle. I'll show you that in a couple of slides. This object here is from a gear manufacturing company up in Lebanon, Oregon. It's called Lin Gear, and they made these demonstration gears out of UHMW. That's a kind of plastic. UHMW stands for ultra high molecular weight. So they're illustrating for their customers how the base circle and the pressure angle works. Here's the slide I was thinking of, where you can see this line that is tangent to the two base circles, and the line between the two of them forms an angle that's called the pressure angle. Now, that pressure angle is kind of some subtle geometry, so we won't get too concerned about what that's about. The main thing you need to know is that so the people at the gear manufacturing company will set their gear cutting machine to match that pressure angle, and you just need to specify when you're ordering a gear what pressure angle you want. And probably 9 times out of 10, you're going to want a 20-degree pressure angle. Don't ask me why. It's just the most common. Probably the second most common is a 14.5-degree pressure angle. And you can see in this picture out of Machinery's Handbook how changing the pressure angle changes the shape of the involutes. That's all we need to say about that. Here's a picture out of Machinery's Handbook. These photos are in the Lin Gear shop up in Lebanon, and it just shows how they go about making gears. So they start with round stock. Here are some big pieces of round steel, several inches in diameter. They slice them into slices and stack up those slices until they're ready to cut the gear teeth. And here is the gear cutting machine. It's called hobbing. When you cut a gear, you are hobbing a gear. And so here in the upper right photo, you see that brass-colored thing is the hobber, and that steel-colored thing is the actual gear being cut. There's some more hobbers. And what you might notice is as this hobber turns around, these teeth on the hobber gradually make contact with the gear blank and gradually cut into it. And I say that because this is a drawing that Lin Gear up in Lebanon made to illustrate how those flat teeth on those gear hobbers come around one small step at a time and gradually cut an involute curve into that gear blank. It's kind of cool. Now, after the gears are made, of course, you always need a verification, a feedback process in anything that you make. And maybe you are in a company where you've bought some gears and your inspection department is going to inspect them for quality and make sure they're okay. See this little can down here? That, I forget what you call it, but it's a chalk-like powder that quality inspectors use for checking things like gear teeth. And the inspector has sprayed that chalk onto this gear and now is mating it with a master gear that's made to close tolerances. And they're turning it around and they're looking to see where is there a wear pattern in that chalk. Is it evenly distributed, or are they finding some high places somewhere? There are also various kinds of official tools that one can use for inspecting gears. These are photos from Lin Gear again, various kinds of tools. Last two slides, I wanted to mention that when you work in a manufacturing company, you will hear people talk about backlash. And backlash, when you're installing gears, is, call it the amount of wiggle room. It's the amount of space between two gear teeth. When you bring these teeth together, how much space is there on one side? And it's important that you have a little bit of backlash, a little bit of space, because if you made the teeth so that they made contact on both the top and the bottom, or the left and the right, if they were metal to metal on both sides, well, the gears wouldn't turn. They would just jam up right away and everything would get stuck right before it broke. So we need a little bit of backlash in there. And the assembly crew, the assembly specialists, will get feeler gauges, you know, those thin pieces of metal, and the engineer will probably specify on your gear drawing what the backlash should be for your particular gear train, and then your assembler will measure in here. They can move the center distances just a tiny bit farther apart to get more backlash, and just a tiny bit closer together to tighten up the backlash. So that's what that's about. Oh yes, and also I wanted to mention that there will be lubricant in here, you know, oil and grease, and having some backlash allows a thin amount of lubricant to coat these gear teeth, which is real important, so that we don't have metal to metal. Okay, there's just a little bit